Hello, welcome to this tutorial. This is a continuation of the simulation we treated last time, which is the NGL fractionation using the turbo expander mechanism. So we will just continue our modeling from where we stopped. Now, in the simulation environment, this was where we stopped the last time. So the next scenario was to add the distillation column that is going to fractionate the liquid products of these two separators. So that's what we are going to be doing next. So we go over to the model palette to get a distillation column. A distillation column. Let's see, where can we get that? From the separator section. Let me see. Okay, this is a distillation column. So the liquid outlets of the two separators are the feed into this distillation column. Let's go back to our problem. Yes. Okay. Now we will need to make an adjustment to the LNG exchanger, because the weighting for the LNG exchanger is simple weighted. The rating, simple weighted. So we need to add that to the LNG exchanger before we continue. I think I omitted that in the last tutorial. So we go to rating. Okay, from the parameter section of design, the rating method is already at simple weighted. It's already at simple weighted, so we don't need to make any changes. So there are other types as well. You have the simple endpoints, you have the EDR, cold wound, and plate film. But we want to use simple weighted for this particular model. So we can now specify the distillation column. Now the outlet of the distillation column is actually the top outlet of the distillation column is actually the inlet of this LNG exchanger. It's actually one of the inlets, so we'll be making that adjustment as well for this LNG exchanger. The top outlet of this distillation column is part of the inlet of this LNG exchanger, and that is what will make the LNG exchanger to solve. Now, so we'll be making that adjustment for this distillation column. Now, this stream that is number 3 is actually the top product of the distillation column, and then this other stream, that is number 2, is actually the top product of this second two-phase separator. So I'll make those adjustments before we continue the simulation. So how do I do this to make it better? Let me see. I reduce the size of this. Then let me see. Okay, I would remove this as well. Break connection. So I'm deleting this guy. Then I would now connect to this guy. I will connect to the top product of this separator. Then the distillation column is the top of this one. Yes. Okay, then for the distillation column, we are making use of, let's check for the distillation column. okay, distillation column specs, you have condenser is full reflux. Condenser is full reflux, right? And then the overhead vapor outlet is 3, right? Because I want 3 to be the overhead of the distillation column, right? So I will just make adjustments to this. Let me push this forward and bring this outside. Yes, so we are good, right? Then what else do we have there? Full reflux. Then we have number of stages. So we'll create energy streams for the condenser and the reboiler, right? Conq. Then the reboiler is repq, right? So we have created our energy streams for the condenser and the reboiler. Then the bottom outlet is, just name it this. Then we now specify our feed streams. Our feed streams is both feeds, right? Both the feed from this separator and the second separator, right? So those are the streams that are our feed. So we have the first one is, let me see. Okay, the first one is leak 1. So we add leak 1 to the feed. Then the second one is V out, right? So V out is the second. Yes, then from our problem statement, the number of stages is 5. So we are supposed to change that to 5. So we have specified our inlet streams, then our outlet streams, the type of condenser, and then the energy streams as well, right? So we are good to go. But from here, I want to change the stages of the feed streams, right? So I change the stage of the first feed stream to condenser, then the second one to main tower, right? Main tower 1, that's the first stage of the distillation column. So we can now make other specifications for the distillation column from the problem statement. You have, okay, so we have to continue to specify the next. We'll leave this as default once through regular high-6 reboiler. Then we have the condenser and reboiler pressure drop as zeros, right? Yes. Then the condenser and reboiler pressure are 2766 and 2800 kPa respectively, right? Now we click on next. Now we don't have temperature specifications, so we just click on next. Then as well as the reflux ratio and vapor rate, so we just click next as well, right? We will be specifying the column duty and rate vapor pressure instead, so just click done, and then we can go into the column environment to make those adjustments, right? So you go to monitor. Here you can add specs, right? So we are specifying column duty, which is this, right? You click on add specs and then you specify which of the specs you want. So in this case we are specifying column duty, right, which the value is 0.001 kg per hour. Let me see, 0.001, enter. So this the duty we are specifying is for the condenser. So you, from here, you choose the condenser before you exit the form, right? So we have specified column duty, then we are going to add another spec for rate vapor pressure, right? So we look for vapor pressure. Okay, you click on column vapor pressure spec and then you click on add spec, right? So we are specifying rate vapor pressure. Then let me see. Okay, so the rate vapor pressure specification is for the reboiler, right? The reboiler, the phase is liquid, and then the spec value is 200 psi. 200 psi, right? So we are good with that as well. Now we have specified all the column specs, right? So we have to activate them before we run our column. So we deactivate these other specifications because they are not specified. We didn't specify their values, and then we activate those that were specified instead, right? So we activate this and this one, right? And then we let it to solve, right? So it has solved, our column has solved, right? It has converged. So we deactivated the specifications we didn't specify, right? And we activated those that were specified, and you see that HiSys estimated the values for the unspecified specifications as well, right? So we can exit this distillation column, right? So you now see that the whole simulation has solved, right? The LNG exchanger has solved as well, because we have been able to fully specify the distillation column and then let it converge as well, right? So that's it. So like I said in the previous video, that this is as we are simulating the process that the LNG exchanger would get fully specified, and it has done so right now. So this this is the initial aspect of the process, the expansion of the gas, right, which produces energy, then the fractionation of the feed, the distillation feed, right? The separation in the distillation column, we are going to be mixing streams 3A and 2A together, right, using a mixer. So we get out a mixer. This is a mixer, right? So we'll be mixing both streams together. So we change the position of the mixer, then we can get out the, let me see. So this will be, we'll create an outlet stream, then the inlet stream is stream 2A and stream 3A, right? So we have this, should be like this, yes, okay. Then now this mixer outlet is what is fed to the compressor, right? The compressor will work based on the energy provided by the turbo expander, right? So we'll be getting out a compressor for this. Right? So we have a compressor here, yes, and we'll be changing the direction of the compressor as well. But does it need changing? Let me check. Okay, let me create an outlet stream first. Let's see, comp out. Okay, yes, so we need to change the direction we need to change the direction of this, yes, as well as the product. So we are changing the direction. Then the inlet is mix out, right? Then what else are we going to do? Okay, so now we have specified the inlet and outlet of this compressor, right? So what is left is the energy, right? The energy of the compressor, the energy stream. The compressor requires an energy stream. Now we'll be making use of the energy stream of the turbo expander, right? Pause. Which is QE, right? QE. So we are making use of the energy stream of the turbo expander. So the turbo expander provides the energy required for this compressor, right? So you click on QE, right? So QE is connected to, yes, it's connected. No, not QC, QE. QE. Yes. So you see that once you connect QE to the compressor, the compressor automatically solves, right? So this expander provides the energy required by this compressor, right? So it doesn't need an extra energy or an energy from outside, right? An additional energy to run, right? So the energy it requires is provided by the expander, right? And that is the main concept of this turbo expander process, right? It is the connection of the expander and the compressor based on the energy produced through the expansion of the gas or the fluid that passes through the expander, right? That is the concept behind the turbo expander mechanism, right? So our comp out is at it's actually at a pressure of 3146 kPa, right? So in this case we want to increase the compressor, or we want to, the compressor outlet pressure, right? So because of that, we'll be adding an extra compressor to our process, right? Because we want the gas outlet to be further compressed, right? To be further compressed. So we will be adding an extra compressor to the process. So we just get one from the model palette. From the model palette, you have compressor here, right? Then we change the direction. Sorry about the increase in size of the flow sheet. Then we are changing the direction, flip horizontal. Then we create an outlet stream and an energy stream for it. So inlet is comp out. Then outlet can be comp out 1. Enter. Then this can be QK, right? So all we need to do is specify outlet pressure, and this should solve. Specify outlet pressure, right? So we are good. So the process has solved, and we have been able to further compress our outlets, right? Our outlet product, we have been able to further compress it to 7,000 kPa, right? The pressure has been increased to 7,000 kPa, but there is an implication of that, because as you increase the pressure of the gas, the temperature also increased to 104.2 degrees Celsius. So because of that, we will be adding a cooler. We will add a cooler we'll add a cooler to the process. Right? So from here, we'll be getting a cooler that we would use. Right? So this is the cooler. So I need to change the direction of this guy. Flip horizontal. Then I bring it forward to somewhere here, right? Then I take this guy up a little. So we are going to be dropping the temperature back to atmospheric temperature, right? So our energy can be cool. I will just use this. Then outlet is export gas, right? Then the inlet is this, yes, right? Then our parameters, delta P is let's check for delta P from here. For the second cooler, delta P is 15, right? 15 kPa. So we specify that 15 kPa. And then what else? So we are dropping the temperature from 104 to 25 degrees Celsius. So with that, the cooler is fully specified, right? So I don't know why let me change the direction of this guy, right? So we have been able to fully specify our product, which is export gas. Then let me drop this so that the whole simulation can be viewed right at once. Right, so this is it. This is this full simulation. Right, this is the full simulation. So this is a simple expander process, right? A simple expander process. You have your feed through the LNG exchanger. Your feed is cooled via the LNG exchanger, right? Because the feed was at 25 degrees Celsius, then it was cooled to minus 50, then it is still further cooled to minus 62 degrees Celsius. Then it is passed through a series of two-phase separators, and you have your turbo expander in between. So the first two-phase separator separates vapor from liquid, right? The vapor is sent through the expander where it is expanded. That is, the pressure is reduced, right? The vapor is at 4960 kPa, right? The pressure is reduced and the volume is increased. The outlet pressure is at 2800 kPa, right? And this outlet gas is now sent into another two-phase separator that separates vapor from liquid, right? Then the two liquid outlets are now sent into a distillation column, right? So that the vapor present in them can be separated from the liquid bottom products, right? Then all these vapor outlets, the vapor outlet of the two-phase separator and the vapor outlet of the distillation column is sent back to the LNG exchanger for heat exchange, right? Then the outlet from our mixer is then sent into the compressor, of which the power of that compressor is provided by the turbo expander, right? The turbo expander. Then the outlet of this compressor is further compressed, right, to the desired pressure, right? The desired outlet pressure or the desired product pressure, right? Right. So we have our product then cooled, right, at the end of the process, right? So this is our product what will I say, product condition, right? Conditions. You have your temperature at 25 degrees Celsius, pressure 6985, then molar flow of 2929 kgmol per hour. Then if you check your composition, right, you have your methane, mostly methane, right? The composition of the product is mostly methane. You have 0.9338, then ethane of 0.0463, then you have a little propane and very minute amount of butane, right? So this is the product composition of this particular process, right? So this is the end of this particular tutorial, right? Hopefully we would have one more tutorial, right, or two more on this particular model, which is the fractionation of natural gas using the turbo expander mechanism, right? So hopefully we would have one or two more tutorials on this, right, in time to come, right? So if you have a question on this particular model, right, on this particular model, drop your observation or your question in the comment section. Like this video, share it with your friends, then follow this channel for more tutorials, or subscribe to this channel for more tutorials on process simulation. Thank you for joining me. Do have a good day.